All right, welcome back to Mr. P Helps with Calculus. This is Unit 4, Day 12, as we're exploring the L'Hopital rule, which is basically a shortcut, a way of finding a derivative when you're given an indeterminate solution. And we'll talk about that in just a second. All right, L'Hopital's rule states that if you're trying to find the limit of a function over another function and you end up getting an indeterminate solution, if you plug whatever that value of a is into this function and into this function and you get 0 over 0 or infinity over infinity or negative infinity over negative infinity, any other, I think there's 7 indeterminate solutions, but these are the ones that you're going to most likely see. If that happens, that does not mean that it doesn't have a limit at that point, not necessarily. What you can say is, according to this rule, is that if you do the derivative of the top and the bottom, that answer will be equal to it, and you will no longer, it's kind of like getting rid of the whole. It's like getting rid of the 0 over 0. It's like getting, crossing it out, and then whatever you're left with is going to be the solution itself. All right, so suppose that f of a equals g of a, and they both happen to be equal to 0. So if you find that this and this end up both being 0 or infinity over infinity, and f and g have to be differentiable, which means they have to also be continuous by definition, then what you can do is just find the derivative of each and then use it. Now, if that doesn't work and you keep getting 0 over 0, just keep using L'Hopital's rule. So basically, usually you won't have to do it more than twice, but you should be able to do it as many times as needed until you get an actual answer is revealed. All right, so here, let's put it to practice. Now, here, first thing I'm going to say right now, and it's going to seem a little bit annoying, I guess, might be the right word, is the fact that, yes, this is what's required on the AP exam. You must prove that it's an indeterminate solution first, and then you must state that you're going to be using L'Hopital's rule. So that's important. They will take off points if you don't actually do all of those steps, because that's proving why you're doing what you're doing without actually having to say that they're equal. You don't actually have to state, let me go back, you don't have to state this. If you just say this, that is like stating this. Now, if you want to state this instead of just saying the name, like if you actually forget, I would assume that would also, I can't imagine anybody actually doing that, but by stating this, that's literally what this means. Okay, so that's why I put that there. So what I'm saying is that this limit is equal to its derivative. So this is literally just the derivative of that, and that's literally just the derivative of that. And then I can plug in, and then I can solve and get an answer of 2. Now, why was I able to do this, though? I need to go back up here, and I need to prove why I'm able to do this. By what I did, okay, the way I did it is I used my limit properties, and I split this up, and I did the limit of this and the limit of that. That's the first thing I did. Then I plugged in 0 into this, and I got here, plugged 0 into this, and got here, and that's how I found that it was an indeterminate solution. And then I went for, I know I did this problem completely backwards, but then I went ahead and did this and find that, yes, there actually is a limit at that value. Just because I got 0 over 0 doesn't mean that there wasn't an answer. And I will just keep doing it until I get an actual answer itself. Same thing, I use my properties to split it up. Then I plugged in my 2's. I end up getting 0 over 0, which tells me that L'Hopital's works. So now I know that the limit of the original equation is also equal to the limit of its derivative. And the derivative of this is here, so that's the derivative of this. And then once I got that, then it's kind of like getting rid of the 0 over 0. You're getting rid of that indeterminate solution by removing that whole by differentiating it. And therefore, plug in 2 in the top and bottoms, and you get a solid answer of 3, just using your algebra skills. All right, another example. This time, when I separate this with my properties and I plug it in, I end up getting infinite solutions on top and bottom, which is also an indeterminate solution. Which means I'm going to use this same rule. I'm going to say that the original limit is equal to its derivative. Derivative of x is 1. Derivative natural log of x is 1 over x, right? So this is still the limit as x approaches infinity. Got to keep it in limit notation. Then I'm going to simplify it down. I honestly could have skipped this because obviously it's obvious that this are equal. But then I can plug in infinity on top and bottom for x's, for any of the all x's, and 1 over infinity, like 1 over a trillion, which is the biggest number I could possibly think of. 1 over a trillion is essentially just 0. 1 over a really big number is essentially going to be 0. And that's what you're approaching. Remember, that's what limits are. Limits are what you are approaching. It's not exactly what it is. All right, let's look at the next question. Same thing, I use my properties. I proved that it's indeterminate. I think I've covered that pretty well. Now, this time I'm going to plug 0 in. Okay, so what I'm saying is by L'Hopital's rule is that the original limit is equal to the derivative of f of x and g of x. So this derivative is here. Make sure you use the chain rule here, right? Derivative of sine is cosine, but you have to also multiply it by the derivative of the chain. Can't forget about that. Derivative of x is 1. Then I plug 0 in for x, and I get my answer of 3. Now, I got one more example for you, and I told you at the very beginning of this video that this could happen. In number 5, I figured out that it's an indeterminate solution. Okay, it doesn't change, hasn't changed at all. I've stated the fact that I'm going to use L'Hopital's rule, and I have found the derivative of this, which is here, found the derivative of this, which is here. I then plugged in 2, and I still got 0 over 0. Since that happened, what I'm going to do is basically find the second derivative of the numerator. Second derivative of f of x and second derivative of g of x gives me this. So this is, I'm not going to go ahead and state that this is equal to this again. I guess, I don't think they're going to require that, but this is equal to this because this is the second derivative of this. Oh, whoops, sorry. I was pointing in the wrong place. This is the first. That's first. So this is first derivative right here. That's the first original function equals the first derivative, which also equals the second derivative. So all of this equals this. This, and this are all equal because of L'Hopital's rule. Then, if I plug in 2 for all the x's, I get an actual answer. Now, I'm going to tell you right now, it's pretty rare that you're going to have to do it more than twice. This is probably the max you can expect to see. But who knows? We have no idea. The test changes every single year. Maybe they're going to give you a question where you have to do it more than twice. I don't think they ever will, but if you have to, then do it. All right, I think that's going to be it for L'Hopital's rule. Thanks again for watching, and I will see you on the next video. And don't hold me to it if I say it incorrectly one of these times. Have a great day.